Hello again. So now that we talked about this homogeneity and we want to use that homogeneity concept to further simplify this equation, so we define two variables and make a change of variables because as we know, um, these two moments, these two second point moments or 2 point moments in a homogeneous flow only depend on their distance, and it doesn't really matter where they are located. So we can use this property to kind of further simplify our set of equations here, which are pretty complicated. Okay, so in order to do so, I define two sets of new variables. One is Kesey. I define it as the sum of two vectors, x and x prime. So x prime plus x. And then r as their distance, which we already defined it here. So it's going to be x prime minus x. Okay? So now I want to rewrite all my equations based on these equations here. Instead of x, I want to x and x prime, I want to use Kesey and r. Okay, so let's do change of variables here. So change of variables. From x and x prime to Kesey and r. Okay. So based on the chain rule, for chain rule of differentiation, we can first calculate the differentiation of, say, because we have here differentiations, right, with respect to x and x prime, k prime. So we can do that here. So let's say for partial over partial x prime I, we know that here x prime depends both on r and Kesey, right? So based on the differentiation rule, we can write this as partial over partial Kesey I, partial Kesey I over partial x prime I plus partial over partial ri, partial ri over partial x prime I. Okay? Yeah. So now what is this? Partial Kesey with respect to x prime I, you see it here, it's just 1, right? Partial Kesey with respect to, if you take the derivative here, it's going to be x prime plus x, and with respect to x prime, it's going to be 1. And how about the second one? The second one, we have it here, x prime, again, it's 1, right? The derivative is going to be 1. So this equals to partial over partial x Kesey I plus partial over partial ri. Okay? So now let's take the derivative with respect to xi. We are going to have a similar thing. But now with respect to x instead of xi, right? So what is the derivative with respect to xi here? For Kesey, it's 1. How about the second one? Here, it is minus 1. Partial r over partial xi, this is minus 1 here. You see it? So this equals to partial over partial Kesey I minus partial over partial ri. Okay? So Again, because of homogeneity, all the derivatives, everything for the mean variables only depend on r, right? Their distance, not their sum. Okay, so all derivatives involving, if we put them into the original equation for the mean variables involving Kesey, are identically 0. And in homogeneous flows again, and homogeneity reduces the 2-point Reynolds stress equation to the following, okay? So because of homogeneity, the only thing that here matters for mean variables is their distance, okay, or, and it's not going to depend on their sum. So now we know that here, based on this definition that we had here, I can write these u prime I, u prime j as bi, j, r, and t, right? So that's going to be the first term that I have, and it's only a function of r. Okay. So for the first term here, I can just use that. So let me write it here. So it's going to be partial bij r and t with respect to time. Okay, and then the rest I put on the right hand side of my equations. So here I have, first I would put these into the right hand side, these two I put them on the right hand side. So let's see what we have here. So we have now triple moments here, so I can use I, K, and J because these are in the x direction, and these are with x prime in the second point, right? So I can use this as bi k j, right? This is going to be bi k j, and this is going to be bi and jk. Okay, so let me write down with another color. Okay. And then we have the derivative with respect to xk for the first term, and we know it's going to be partial over partial ri. And then with the second term with respect to x prime k is going to be minus partial or over partial I. Okay. So let me see if I've done it right. X prime, and then so x prime is going to be, yeah, so this is going, so then we need to, I also want to do the transformation from xk and x prime k to Kesey and r. So we are going to get this. We are going to get partial over partial r. I put it on the right hand side. Bik j r and t minus bi jk, r and t, and this is going to be these two terms. Again, the Kesey, because here we have homogeneous flow. In a homogeneous flow, these triple moments are not a function of Kesey. They're the sum of the vectors, the only function of their distance. So we can neglect them. And so then we put this on the right hand side. And if you put it in the right hand side using these transformations that we have here, we're going to get this. Okay. So now let's go to the the first term on the right hand side we already had, which was this term. So now we have here the b between the function that we define, p and j. For the first one, it's going to be b, p, and j, and for the second one, it's going to be b, p, and I. Okay. And so I'm going to write it because plus 1 over rho, and then we have that Ri for the transformation. So it's going to be, if you do the derivation, it's going to be partial bpi r and t with respect to Ri minus partial bi and p r and t with respect to, let me see, rj. Yeah, we have here rj. Yeah, first one is I and second one should be rj. And then the last term that remains is the viscous term here. So again, these we define as bij's, right? We defined it here based on bij's. So it's simple. We can just put it there. And then also we have ij, they are the same. And because this is a second derivative, if you take it 2 times, these minuses are going to be plus, minus times minus is going to be plus, so we are going to have 2 terms here, which are going to be plus 2 nu partial square bij r and t over partial rk squared, right? I have 2 terms here, rk, they are going to be rk, and then they will add up. They are the same, bij. Okay, so you see now things are getting a little bit more simplified. And I still want to make this even further simplified to be able to understand something out of it, okay? So one thing that I want, these are the 2 points Reynolds stresses for all the terms, like it's going to be B for all the velocity components, B12, like B13, right? All these different velocity components, like let's say first U prime, V prime is going to be B11, right? B12, say. So it's going to be B12, and then you want to U prime, W prime, 2 other things going to be B13, right? So these are for all velocity components, 3 velocity components. So one thing that I want to further simplify is to only look at, let's say, U square, V square, W square. So let's say we are interested that's going to further simplify that. If we just look at the trace, so if we are interested in u1 square bar, u2 square bar, and u3 square bar, right? So here, let's say I wrote it in terms of w. Can write it like in this way: u1, u3, and here we have u1, u2. Okay. So instead of these, if we just look at u1 square, u2 square, u3 square, just those terms like u1, and let's say the correlation of u1. I think it's better to define it this way. Based on what we have defined, so u1 and u1 prime. So the correlation, autocorrelation terms between the signals themselves, u2 prime, the same velocity component. So we don't look at the cross correlations, just the autocorrelations between the velocity components, the same velocity components across the flow. Okay, so if we just focus on those these variables instead of all the cross correlations. So let's focus only on the trace of these Reynolds stress tensor by setting I equals to j here. So if it's just set I equals to j, then things are going to be much simpler. And one thing that immediately we find is that the pressure term is going to drop. Why? Because we are going to have here, we have the pressure term, right? So let's write it down. So if we set I equals to j, the second term here we had rj, so it's going to be Ri, and then everything here is going to cancel out. So one thing I think here I need to write this as J. So let me write it down. This is BPJ. Let me make sure that I've not written it wrong, because we had the pressure term here, so it should be P, BP, and J, and then with respect to XI, it's going to be minus that. So yeah, then we have the plus sign. So that's correct. So it should be like this. So if we now change J to I, so these two things are just going to be equal to each other. So this term will cancel out, and so pressure terms drop, which significantly make our life easier because we get rid of this term. If we only look at the trace of this tensor. Okay, so we are going to we are left with this. So if we just set I equals to j, I can just write it down. So let me copy it here. Then we have this on the left hand side, and then on the right hand side we have this. So let me just copy it and then set I equals to j. Then here we have this. Okay, so let me now set I equals to j in all the terms here. So remove j in all the terms. So we have bii, biki, biik, bii. Okay. So now we have simplified the original equation into these only few terms. Okay. So the next step I'm going to do to again further simplify this equation is to do Fourier transform on this equation. And the reason I'm going to do Fourier transform is because Fourier transforms have a property that will convert the derivatives here, the spatial derivatives, they will convert them, if I do the Fourier transform in space, into multiplications, which are going to much further simplify these equations. So let me first briefly review what are Fourier transforms for those who are not, who don't fully remember that. This is again from your calculus. So Fourier transforms So Fourier transform is a mathematical transform from physical space to frequency space. Okay, so it's just a simple mathematical transform. So it can be we typically do it like for complex Fourier transforms based on integrals. So say we have a function f(x) and we want to do the Fourier transform on that. So for this function, the Fourier transform, we show it with ft, Fourier transform of fx from the physical space, and then we show it with f hat k, and this equals to 1, this is the definition, 1 over 2 pi, the integral from minus infinity to infinity of fx e to the minus I kx dx. And k here is wave number. So if you do this, you are going to get a function which depends on k, or wave numbers. So we have actually converted the function and transformed it from physical space in x into the frequency space k. Okay. So then we can also reconstruct the original signal from, say, this function in Fourier space by doing an inverse transform. So we define an inverse Fourier transform as this. So we can reconstruct fx if we just do Fourier transform, the inverse Fourier transform of this function f hat k, which is defined as integral from minus infinity to infinity of f hat k e to the I kx dk. Okay. So if you do that, then you can reconstruct your original function. So this is what's the use of this? The use is that Fourier transform has some properties that are going to simplify PDEs. So you can show that, and I'm not going to go through it in details, that the Fourier transform of the derivative of x, f prime x, is ik times the Fourier transform of fx. And similarly, the Fourier transform of the nth derivative of x, like dfn over dxn, equals to ik n Fourier transform of fx. So this is going to really simplify our equation here if we do the Fourier transform, because then these terms, these derivatives, become just multiplications like here in the Fourier space. Okay? So let's do this trick. But before that, let me also define 3D, three-dimensional Fourier transforms. So these were one dimension. We just do it in one dimension. But we can also do three-dimensional Fourier transform. So let's say Fourier transform of Bij or t, this function that we define, we just show it as Fij k, define it as this, which is going to be, we just need to do this in all the different directions. So we have 1 over 2 pi cube, and we need to do it in x1, x2, x3. So we are going to have 3 integrals from minus infinity to infinity of e to the minus I from k1, k2, k3. So km, rm, so it's going to be k1, k2, k3 of bi and r1, r2, r3, which are in 3 dimensions again, ij r dr. Okay, so r1, r2, r3 in 3 dimensions. So 3D, three-dimensional Fourier transforms. Okay, so now that we define these three-dimensional Fourier transform, now let's take the 3D Fourier transform of the equation that we had here. Okay, so if you take the Fourier transform of the first term, what we are going to have? If we take the Fourier transform of the first term in space, based on the definition that we had here, it's going to be this term Fij, and here it is, because it's II, so it's going to be Fii. So I can just remove here this and write this as Fii k and t. Now we are in the wave number space, so it's going to be k rather than r, t, and time. We have time too. Okay, so I'm just doing the Fourier space in 3D space, in the three-dimensional space, and not in time. Okay, but you can also do it in time, but I don't want to do it in time. So then for the second terms, these terms, I will just write them as GII, and then I will say what does that mean. And then for the third term, we are going to have, we have this, so let me do it here and let's see what it is going to be. So if we do the Fourier transform of this is going to be based on this property I showed here. is going to be ik to power 2, right? Ik to power 2, because we are taking the second derivative. So it's going to be 2 nu ik to power 2 of fii kt, right? So let me just write it down. 2 nu ik 2 fii knt. And we know that I to the power 2 is going to be minus 1, so it's going to be minus k squared actually. Okay. So let me define what is GII. So GII is basically GII of K and T is going to be the Fourier transform of these terms, right? So we know it's, because it's partial or partial r, if you take the Fourier transform of this, it's going to be, we are going to have ik, right? Ik from here, because it's the first derivative, and then the other terms, right? So I just write it down here. It's going to be ik l. We have triple moments, I, this il, I minus fi l I. I think this should be I. Let me make sure. First one is IL. This should be I and IL. Okay. So this will further simplify our equations. So let me make sure. So we have IL, I and LI. Okay, so now this is going to much further simplify our equations. Okay, as you see, now we don't have any derivatives anymore. We don't have any derivatives. So everything is except partial t, which I keep it because I want to talk about it. But except that, all the other terms, we don't have any spatial derivative. This is a better way to say that. We don't have any spatial derivative, so we got rid of those partial over partial r's, and we got to this simple equation. So the next step that I'm going to do, and I will do it in the next lecture, I'm going to further simplify this equation by defining a 3D spectral function, because FIs are still a little bit difficult to understand. What does like FII mean? So I'm going to define this 3D spectral function. And that function is going to give us a very famous equation in turbulence which we are going to investigate how like dissipation and transport terms actually work in turbulence, and that will be a very simple equation that we are going to learn and gain some insights into the turbulent processes in flows. So let me briefly review what we did today. So we started with the dynamics of homogeneous turbulence. So we defined these instantaneous fluctuating velocity at x and x prime. So we did some manipulations, and after some manipulations, we got to this averaging and assuming no mean velocity, we got to this equation for the for 2-point Reynolds stress equation. Okay. And then we assume turbulence homogeneity to simplify our equation. So we know in a homogeneous flow, the mean variables only depend on the distance between two points, and don't really depend on their location. So we use this concept and we define two sets of variables r and Kessi to change from that x and x prime to these new sets of variables, and then we finally got to this equation here. And then to further simplify this, we only were interested into the trace of this Bij tensor. So we only wanted to look at the autocorrelations of the signals velocities with themselves. So we only focus on the trace by setting I equals to J. So one advantage of this is that the pressure term drop, and we get this equation, which is a much simpler equation than the original equation. It's only a function of r and time, the distance between 2 points and time. And then we defined Fourier transform and treated Fourier transform to start further simplifying this equation and get rid of the spatial derivatives. So once we do that and take the Fourier transform, 3D Fourier transform of the equation, we get this equation, which is now much simpler than the earlier equations, right? So this equation, we are going to investigate it further in the next lecture, where I am going to define a 3D spectral function to further simplify this equation and to gain some insights into the dynamics of this equation. Thank you very much, everyone.